Okay, so in this video, we're going to go through Chapter 2, Sections 2.3 limits and 2.2 limits and 2.3 continuity. Okay, so our textbook states the following. From the calculus perspective, a basic aspect in the study of functions is the analysis of how changes in inputs. Remember, that means x values. So changes in x's affect changes in the corresponding outputs. So that's the y's. Suppose we choose the inputs, the x, getting closer and closer to a given number. So then the question is, if that's happening, will their corresponding outputs get closer and closer to some number as well? So this is the whole focus on limits, just getting closer and closer. Okay, so the basic definition, let g of x be a function and alpha a number. We say that the number L is the limit of g of x. Okay, so that means that the number L is the y, right, of g of x, as x approaches some alpha, provided that g of x can be made arbitrarily closer and closer to L by taking x sufficiently close but not equal to a. Okay, so the long and short of that is this. As our input approaches a, our output will approach L. That's a limit. So now let's look at this function to the right. It's a very basic function. So this function to the right is this function. F of x equals 2x minus 1. We know from the last section that that's a linear function. It's also a polynomial of degree 1. So let x approach 4. Okay, where is 4? 4 is right here. So x is approaching 4. What's going to happen as x approaches 4? Well, if you just go up, you can say, oh, well, it's just going to, y is going to just be 7. Okay, that's the idea. But as you approach 4, you can approach it from two different sides. So you can approach it from the less than 4 side. Okay, so if you're approaching 4 this way, that's called approaching it from the 4 less than 4 side, as opposed to approaching it from this side, which is approaching it from the 4 greater than 4. Okay, look what's happening. You are going to climb up this x-axis, or this function. So as you approach from the left, which is the less than 4 place, you're approaching here. Don't get there yet, just approach it. Okay, so I'm getting closer and closer. Now let's try to approach it from the other side. Coming down lower and lower, and I'm approaching here. So where am I approaching? As I come down, I'm approaching 7 from both directions. That's what's happening with the limit. That's what a limit is. So how can I write this expression to indicate what I'm doing? I would just say the limit as x approaches 4 of this function is some L, and then I've just discovered that that sum L, which is the limit, is 7. Okay, that equals 7. So that's your y value. Okay, that's the essence of what we're doing. So let's look at it in terms of a table. If I say evaluate a limit algebraically using a table, this is what you're going to do. It's the exact same function. I determine the limit. Remember, x can be close to 4 but not equal to it. Okay, so let's approach x from the bigger than x position. So look what I'm doing. I'm starting at 4.1. Okay, that's bigger than x, not by much, but it is coming from that right side. So I'm coming from this side. So plug in your values. 2 times x, and x is 4.1, minus 1, and that's going to give me a value of 7.2. Remember, those values are your y values. Get a little bit closer. I'm coming from the right side, from the higher numbers coming down. Okay, so I'm coming this side, going this way for the pink. Okay, so 2 times Let's make it 4.01 minus 1. That's going to equal 7.002. 2 times, get a little closer, 4.001 minus 1. That's going to equal 7.002. This one only has 1 0. I apologize. And then go a little closer still, 4.0001 minus 1 gives me 7.0002. I'm getting closer and closer to 7. Clearly that's where I'm heading. Now go the other way. Let me change my color to green. I'm going to come from this direction. So if I plug in 3.9, I'm going to have 2 times 3.9 minus 1. I'll tell you that's going to be 6.8. Then plug in 3.99. That will give you 6.98. Plug in 3.999 with your calculator. You're going to be getting 6.998. And the last one, really close but not quite there, is going to give you 6.9998. Okay, so if you look at it from the left and from the right, what number are you approaching? And clearly you're going to say that it is 7. Okay, so just a point to note going forward. We can say that a function has a limit if, when you approach from the left and the right, you approach the same number. That terminology is coming at us in just a second. Okay, so what do you think is going to happen if you do the same thing as x approaches 3? Same function. What do you think is going to happen? Look what 3 is. I'm assuming that from the left and from the right, I'm going to approach 5. So this is going to be 5. I'll tell you all the values here. Plug in 3.1. You get 5.2, 5.002, 5.02, 5.002, 5.0002. And then from the left, remember this notation. These are bigger numbers than 3. These are smaller numbers than 3. So if you go right and left here, I'm going to start out 4.8. I'm going to go all the way down and get 4.998. You get the sense of it without me filling it all in and wasting your time. Okay, so what value you're approaching? Clearly we're approaching 5 from the left and from the right. So that's a good situation. Okay, so that's evaluating limits algebraically, and I kind of used the graph as well. But what if we didn't have any formulas? We're just going to evaluate this graphically. So what could you say? Look at the limit as x approaches 4. So if I'm approaching it from this direction, which is the smaller numbers, right? So I'm approaching from smaller numbers and going higher. That's from, so let me put that way. That's from the 4 negative side. Okay, so 4 negative side. What do I approach? Well, as I get on this function, I'm going higher and higher, right? Getting closer and closer. So what am I approaching? I'm approaching a y value of 6. Now notice there's a hole in this function. So I don't actually get there. I approach it, but there's not a value there because that's why it's a hole. Let's approach the other way. So change colors. We're going to approach this way. You're on this function. This is a piecewise function. Okay, I'm approaching. When I approach from the positive side, look what happens. I'm approaching a y value of 8. 8 and 6 are not the same number. Therefore, you would say that the limit, so the limit does not exist. And we'll say DNE for that. Because you have to approach the same number from the left and from the right. Okay, so the kind of function this is a piecewise function. Look at the second one. We're going to try to approach 4 again. So approach it from the lower than 4 side, and then approach it from the higher than 4 side. So, and I should probably change colors. So let me get rid of that color. And we'll say, okay, we're approaching 4 from this lower than side, and we are aiming on 4 on the y-axis. Let's approach it from the greater than 4 side. That means we come down this curve, and look, we're approaching the same number. So we can say the limit as x approaches 4 equals 4. So the limit exists, right? Now notice you have exists. Let's just say we have a limit. Okay, so we have a limit. Notice that there's a hole in this function. So this is a hole. So I have a limit, but if this is an f of x function, f of 4 does not exist. There's no value. But the limit of the function of f of x as x approaches 4 equals 4. Okay, you don't have a function value there, but you have a limit. Okay, let's look at the next one. So we're trying to approach to this side this time. So if you are approaching 2 from the less than 2 side, you are on this curve heading this way. You are heading towards negative infinity. If you then try to approach 2 from the greater than 2 side, you are heading up this curve. You are heading towards positive infinity. You are heading 2 different places. Therefore, by definition, your limit does not exist. Okay? So to check the limits, this is our procedure. Check the limits from the right and from the left. If limits do not approach the same value from the left and the right, then the limit does not exist, and this can be written as DNE. Okay, so I said pick some. Let's do some graphical analysis. So I want to say the limit as x approaches 1. So we can say that this way, the limit of f of x as x approaches 1. Okay, so here's where the 1 is. Let's approach from the less than 1 side. So you're coming this way, and you're trying to approach this value here. As I get closer and closer from the left, I approach 3 for the y value. Remember, the y value is your limit. Let's go the other way. Let's approach it from the more than 1 side. You're going to climb up this curve, and you're still approaching 3. Because you're approaching the same number from the left and to the right, you can say the limit as x approaches 1. Notice I don't have any plus or minus notation there. That limit equals 3. The way I knew that was I analyzed it from the left and from the right. Let's do the same thing for this next one. What's the limit as x approaches negative 1? So here's where negative 1 is. Here's where my function is, right here, okay? So approach it from negative 1, the smaller side. I'm aiming down here, and I'm approaching a y value of 2. Come the other way, approach from the negative 1 greater than negative 1 side. I'm going up the curve. My end result is still getting closer and closer to a y value of 2. So we can say the limit of this is a g of x. So let me write this as a g of x. As x approaches negative 1 equals 2. So that limit exists. Okay, what about the last one here? I have a rational function. So those first two were polynomial. This is a rational function. As x approaches negative 2, so if I approach from the negative 2 negative side, which means I'm picking numbers that are smaller, and I'm aiming to get to an x value of 2, I am going up this way, but never actually getting there. If I approach instead from the -2 positive side, I am going down here, and I'm approaching negative infinity. Okay, so I can say that the limit, this is an h of x function, as x approaches -2, does not exist. I'm heading two different places, positive infinity and negative infinity. Okay, so a word about this. I'm going to use the terminology that if you do not approach a number, your limit does not exist. Well, will I do that? Well, let me go with the textbook. Okay, our textbook says this, that if from the left and the right you approach infinity, they say the limit approaches infinity. Okay, many other textbooks, if you are approaching infinity, because you're not approaching a number, they say the limit does not exist. So I'm going to go with our textbooks just so it's common between what you're reading and what I'm saying. Okay, but know that in other textbooks, they may have a different terminology. Business calc tends to say the limit does not exist if it approaches infinity, whereas what I've seen before is that like AP Calc tends to say the limit is infinity. Now here, because you're approaching two different versions of infinity, you are not approaching the same place, and therefore your limit does not exist. Okay, limits are confusing the first time through, so that's okay. Feel free to feel confused, and then you'll get out of it. Okay, so then there are 6 limit theorems. Now we're going to use this to a limited extent, no pun intended. Okay, the limit of a constant is the constant. Okay, so how is that? As x is changing, if you're saying I want to find the limit of 7 as x gets closer and closer to whatever, it doesn't matter. The limit of 7 is going to be 7. 7 is not going to vary. It's a constant. Okay, so the limit of a constant is the constant. The limit of a constant and a function is the constant times the limit of the function. Okay, so remember the constant has no limit itself. So you can pull it out in front and then take the limit of the function and multiply it by the constant, and you're there. Okay, if r is a positive constant, then the limit as x approaches a of f of x to the r is going to be able to be brought inside and raised to that r. And we're going to do this in a second. Okay, remember this notation means f of x plus g of x. So the limit of a sum is the sum of the limits. Don't let the notation fool you out. If you know the limit of f of x is something, and you know the limit of g of x is something, add them together, and if both limits exist, then you have a finite answer. The limit of a product is the product of the limits, same thing. If both limits exist, then you have a finite answer. If one of them does not exist, then you don't have a limit. Also, the limit of a quotient is a quotient of the limits, same thing. Remember, the limit is also the denominator, which is the g of x. That limit cannot go to 0, otherwise it does not exist. Okay, so how can I use this? If I want to figure out the limit as x approaches 3 of x cubed, I'm going to bring the limit next to the x. My next step is just going to be direct substitution, plug it in, and you get a number 27. That's your limit. Okay, that's by direct substitution. Okay, so here I did this theoretical approach, and then this is the direct substitution. Okay, next one. The limit as x approaches 2. So here's a constant, pull it out. Then the limit of x, and then you're going to square it. So you're basically plugging 2 in. We're going to do that down here. The limit of 7 is a constant. That's always going to be 7. So that's going to be 7. this is going to be 5 times the limit of x. So if I have x is 2, I'm going to plug in the 2, and then I'm going to square it. And then by direct substitution, I'm going to get the answer as 27. Okay? So really, we're applying the theory a little bit, but our method will be direct substitution. Okay, so x approaches 1. I pull the limit. I'm taking that is squared now, plus the limit of a constant is just 8. Raise that whole thing to the 1/2. What do you get? So basically plug in the 1. So 1, take your 1, that's your limit, square it, add 8, and then take the square root of it. That's raised to the 1/2 power. That's important to know. Remember, your index number is a 2, so you're raising it to the 1/2 power. So that's 8 plus 1 is 9, and the square root of 9 is just going to be 3. Okay, next one. The limit as x approaches 5 of 4 times x squared. What would I do? So I would take 4 times the limit of x as x approaches 5, and then I would square that. Okay, so that's going to be 5 squared times 4, which is going to be 100. Okay, so technically, let me go back to this last one. This should be plus and minus 3 because you can get 2 answers there when you take the square root. Okay, so in these cases, the functions have a value at the x selected, and the value is the limit. So there's no holes, there's no asymptotes, there's no special circumstances, there's no piecewise functions. Okay, so now sometimes you cannot do direct substitution. So there are little algebraic tricks that you can do. And this is some examples. So when dealing with rationals, if I tried to plug in 4, I get a 0 in the denominator. I can't do that. So we're going to instead do an algebraic manipulation. Now, what does this function look like, by the way? So it looks like something like this, just so you can see what's going to happen. So this is going to look like 1, 2, 3, 4, and then 1, 2, 3, 4, 1, 2, 3, 4. That's my 8, 4, 5, 6, 7, 8. Okay, and this is 1, 2, 3, 4. Okay, let me show you the algebraic manipulation. Right now, I know that I have a hole, or I can't value, right? So 4 is not in my domain. That's my takeaway. Look at this algebraic manipulation. Before taking a limit, what they want you to do is factor where you can. Factor and cancel. Now take your limit. Okay, so because we're not getting the function value, we want the limit. That's what the function value approaches, not necessarily what it equals. So take this limit, and we're going to get that limit is 8. Well, how did that possibly happen? Well, at 4, I have a little hole. So this is my scenario. This is what my function looks like, but it has a little hole. So as I approach from the left and from the right, so I'm approaching 4 from the less than 4 position and 4 from the greater than 4 position. And either way, I'm approaching a y value of 8. So my function does not exist because I have a hole when I plug in 4, but I can still get the limit. So the limit and the function value is not always the same. Okay, so this is one algebraic manipulation, fancily called factor and cancel. Okay, so this is called a removable discontinuity. And that means that even though I don't have a function value there, I can still get my limit. Okay, so that's one thing that's kind of cool. So if you have a rational function, that's your approach. How do you deal with radicals? Because I have the same thing going on. I have a radical, but I also have a rational. So it's a combination of a radical and a rational. And look what's going to be the problem. I want to see the limit when x approaches 0. Direct substitution is going to make this undefined. So I have to eliminate the radical, and I'm going to take the limit. So I'm going to eliminate the radical and eliminate the denominator as well. So what will I do? Because I like to have that x cancel with the x on top, but I cannot in its current form. So I'm going to do another algebraic manipulation. This is dealing with conjugate pairs. So I'm going to show you what that is. So you would write this the way it is. Okay. Now you're going to multiply this by a fancy 1. And my fancy 1 is going to be derived by taking what I see in my numerator, but having the opposite operation. Now, how can I just come along and do this? You can do this because this expression right here, that's just a fancy 1. And I can always multiply by 1 and not change anything. Okay, so I'm going to FOIL this. Okay, so when I FOIL, I multiply the first terms, which are the two radicals. When you have the same radicals, when you multiply them, you get the term inside without the radical. Okay, then you're going to do your outer ones, which is radical x plus 2 times 2. So that's going to be what? So what's that going to be? So that's going to be, I have this, then I'm going to have this, and I have outer. So I do that, and I get 2 times radical x plus 4. Okay, then I'm going to do inner. Inner is going to give me negative 2 times radical x plus 4. And then my last is going to give me a negative 2 times a positive 2, which is a negative 4. Okay, so what do I see? Oh, then let's do the denominator too. Let's not lose our head. Okay, so I have x times that. So this is radical x plus 4 plus 2. Okay, so let's keep going this way. Look what happens. These guys right here, this is opposite this, they cancel. Let's now rewrite what I have. I have x plus 4 minus 4 over x times radical x plus 4 plus 2. Okay, what gets dropped now? These 4's get dropped. Once you have those 4 drop, I now have x over x, and then don't multiply these out because it's not going to make your problem easier. What gets dropped next? These get dropped. Now you have 1 over radical x plus 4 plus 2. And now it's safe to plug it in. So take the limit now as x approaches 0. What do you get? 1 over radical 0 plus 4 is 4 plus 2. So that's 1 over 2 plus 2, which is 1 over 4. So that's your limit. This was the conjugate pair approach. And I did it when I had a radical in my expression, and I could use that knowledge of getting rid of the radical by multiplying by its conjugate pair to allow myself to get rid of the x. Okay, so that's how I do that. And I wait, and I don't take the limit until I get here. So even though I have a limit of 1/4, at x equals 0, the function does not exist, okay? It doesn't have a value there, but it has a limit. Okay, Now this is another little concept. We were doing, up to this point, these were, so let's see. So this was limits as x approaches a number. So a real number, okay? This is limits as x approaches infinity. Okay, that's not a number. Remember, that's a concept. So I want you to think about horizontal asymptotes. So let's do a visual. What if I said the limit as x goes to infinity of some function is 4? What would that look like? Well, where is 4? Remember, 4 is the y value. Here's where 4 is. What function would have a limit of 4 as x goes to infinity? Well, how about this function? Because as x is getting, hold on so long. As x is getting bigger and bigger, what's happening is my function's approaching the y value of 4. That is the limit as x goes to infinity. Let's do another one. What would a function look like if the limit as x went to negative infinity, so smaller and smaller, is negative 1? Well, where is negative 1 for a y value? It's right here. So what could that function look like? Well, one option, and it's not the only option, it could come down from here and go off to negative infinity this way. That's one option. What's another option? Couldn't it come this way and go off to negative infinity this way? So you have many options. Same thing for the first one. Wouldn't this satisfy that requirement? As long as x gets bigger and bigger in the first case, your y is going to settle in and be very close to equaling 4 in the limit. Or in the second case, as x gets smaller and smaller, tinier and tinier, more negative and more negative, I am zoning in on a y value of negative 1. Will I ever get there? No, but that's the limit, okay? That's where it's getting closer and closer and closer to. Okay, we have some algebraic examples too. What if I say I want you to tell me the limit as x goes to infinity of this first function? Well, since I only have the x in the denominator, you could technically at least visualize plugging in infinity squared plus 3. Okay, what does that look like? It's like a crazy thing. But what does that look like? Well, this is 3 over a larger and larger and larger and larger number. What is that going to get you? 3 over a huge number is basically 0. So that's just doing it intellectually when you only have x in the denominator. So when I say when x is only in the denominator, you can visualize it that way. What's an algebraic manipulation? An algebraic manipulation is divide all terms by highest power of x. Okay, so I am going to have to do that algebraic manipulation. I'm going to take my 3, divide that by x squared. Then I have x squared over x squared plus 3 over x squared. So in the limit, doesn't this 3 over a huge number go to 0? Doesn't this go to 0? But doesn't this go to 1? So that gives me 0 over 1, which equals 0, which is the same thing I got when I did it theoretically. Okay, look at this one. For the second one, I have x in the numerator and the denominator. So having infinity over infinity doesn't really help me understand what's happening in the limit. So do our manipulation. That's divide each term by the highest power of x. So before I take the limit, let me change color so you have a little contrast. Before I take the limit, I'm going to say 8x divided by x minus 5 over x over 2x divided by x plus 3 over x. Okay, what can I get rid of? These x's cancel, these x's cancel. Okay, take your limit. Do you agree that this term, 5 over a huge number, is going to be approaching 0? This one will as well. What about these? 8's going to approach 8. 2's going to approach 2. So you get, in the limit, 8 plus 0, 8 minus 0 in the numerator over 2 plus 0 in the denominator. That's going to equal 8 over 2 or 4. So limits are kind of fun. So again, it's helpful to view taking the limit as x approaches infinity as finding the horizontal asymptote. I know the horizontal asymptote in this case is the line y equals 4. So that's my horizontal asymptote. In this situation, I know my horizontal asymptote is the line y equals 0. What's the limit? The limit's 0 here. The limit's 4 here. Okay, but it's the same value that the horizontal asymptote takes. Okay, so that's the end of limits, which is kind of fun. We're not going to go crazy with it, but I do want you to be able to do both of these algebraic manipulations, be able to do direct substitution, which is right here, and be able to do the limit as x goes to infinity, either graphically or using the divide by the highest power of x rule. Okay, so now we talk about continuity. So a function is considered continuous at x, provided that its graph has no breaks or gaps as it passes through that point. Okay, can you identify the reason why the following graphs are discontinuous? So I'm looking at all of the x's. So let's say I'm going to try to draw this graph. I can draw this piece, but then I have a problem. I can't keep drawing it without picking up my pen and then drawing the next piece. So if you're drawing a function and you have to stop what you're doing and then pick up your pen and move to a higher level or a different spot, you have what's called a jump discontinuity. Okay, so those graphs both have jump discontinuities because you cannot finish the sketch without lifting your pencil. Okay, so let's see what we have here. So they are telling us we have an infinite discontinuity at x equals -1. So look at -1. When I am approaching -1, I'm going to positive infinity here. When I approach it, when I approach it from the less than -1, I go to positive infinity. When I approach it from the less or the greater than -1, I go to negative infinity. That's a infinite discontinuity at x equals -1. But then right here at -7, when I have this hole, this is called a removable discontinuity. And we had discussed that in the notes. So notice the difference. A removable discontinuity, the function has a limit there. Its limit is the y value where the hole is existing. An infinite discontinuity, you're approaching two different infinities and you don't have a limit. Okay, removable discontinuities, they have a limit. Okay, they have a limit. That's the difference between the two of them. Okay, I think I said that. Okay, so that's how that's working. Okay, so that's basically it. Okay, I want you to understand that continuity means that you can draw the whole sketch without picking up a pencil. If I say to you, let's just talk about this for a second. is this graph right here continuous at x equals 1? You would look there and you would say yes. But is it continuous everywhere? You would say no, because you have a jump discontinuity. Okay, over here, I want you to recognize holes, a round circle. That is a removable discontinuity. Whereas the other asymptote, that vertical asymptote, is a non-removable discontinuity. That's an infinite discontinuity. Okay, these are the videos that will also support us in this endeavor to understand. There is limits of combined piecewise functions. That's a good one. Direct substitutions, more about piecewise functions. So between those videos and my notes that you just had and the textbook, you should be okay. If not, just let me know and I can help you further with it.